Hey, good afternoon. My name is Mulder, and I want to welcome you again for this presentation in our series for AI for Aviation Sustainability. First of all, please note that this webinar is being recorded. Today's presentation is called Privacy Attacks of AI Learning and Algorithms, and the presentation will be given by Saba Amiri, who is currently working as a PhD at the University of Amsterdam. Questions can be asked during the presentations through the Q&A section that's inside the Blue Jeans interface, and we'll try to answer those questions in between, if appropriate, and at least also at the end of the presentation. Okay, I will now give the floor to Saba.
Thank you. Can you hear me? All right.
Yes, we can.
Okay. Perfect. So, hello everyone. My name is Saba. I'm a PhD student at the University of Amsterdam. It's very exciting to be here. I'm very happy to be here with you guys. And today, my presentation is on privacy preserving machine learning in general. It is good to be, well, I'm not actually back at the KLM, but it's good to be here. I used to work here part-time, and well, I had a wonderful experience at the KLM. So a shout out to my friends in the marketing science team. And let's start. The title of the talk, actually, I changed it to Privacy Machine Learning because I wanted a generic enough title that would include the broad range of subjects that I'm going to talk about today. This is by no means an in-depth talk about any of the stuff that I'm going to describe. This is just more intended as providing a big picture of the privacy problems in machine learning systems and some of the solutions that you might be able to use to circumvent them. So I will start with giving you the basic setup of what I'm going to work on. Then I'm going to describe privacy attacks against machine learning models, so vulnerabilities of machine learning models. So the scary stuff here. And this will then rationalize me preaching that we need to use some kind of privacy preserving mechanism to defend against privacy attacks. And then I'm going to introduce differential privacy as a very strong set of standards that we can adhere to make sure that your machine learning system is privacy preserving. And lastly, I will very briefly introduce the research that we're doing at the University of Amsterdam. I'm part of the M&S group at the Informatics Institute of the University of Amsterdam. So the basic setup is this. So my work is part of the EPI project, Enabling Personalized Intervention. It is about my very broadly, my research is into enabling privacy-preserving distributed machine learning on a set of disparate data sets. So we're working in medical use cases. You can learn more about the project and the work of both me and my colleagues in this website here. So the basic setup is like this. So we have a bunch of private and distributed large data sets on different hospitals. And we want to train a machine learning model on all of these data sets without forcing the hospital to share the data with each other or with a central server. So the initial solution has been in the past to, as I said, accumulate data. So gather all of the different data sets together in one place and then train a centralized model on all of the data. This poses several challenges. Well, you have privacy challenges, you have communication problems, and all of these would basically stop you from gathering all of these data sets and you know asking the data holders to share the data with you. So the solution to this one is, again, instead of bringing the data to where the computation is happening, to bring the compute to where the data is residing. And one of the, this would be distributed machine learning, and one of the most famous algorithms or paradigms for distributed machine learning is federated learning. In this part of the talk, I'm going to very briefly describe the federated averaging, which is one of the most widely used flavors of federated learning. And I'm going to describe it in our domain. So the domain that I'm working on, so this is medical domain, but can easily be translated to other domains. So you have several hospitals, and each hospital has a data set of patient data. So this could be like thousands or even millions of patients' data. You have some patients who could have some small personal data sets. These will be much more smaller than the data that is residing in the clinic, but still, this could be something that the patients hold on to and don't share with the hospital. You have a research center, and the research center wants to train a machine learning model on all of these, distributed data sets without having direct access to the data. What you do is, and keep in mind that for the sake of simplicity, anytime I speak about machine learning in this talk, I'm talking about deep learning specifically, but this is easily extendable to other types of machine learning. So for this one, let's assume that we're talking about a deep learning model. What you do is in the research center, you design your model, your architecture, your hyperparameters, everything. You will initialize the model with some random processor, whatever you prefer. You send this initialized model to all of the data owners. So each entity that has access to its own data will have access to this to a copy of this model. Next, each data owner will do a local training cycle. So they will train this local copy of the model on their local data set. And then they will send the parameters of the model back to the research center. And now the research center has access to several sets of different parameters from data owners. The research center somehow combines them together. So, for example, for federated averaging, it does the weighted averaging, and there are other methods of federated learning that do other things. And but regardless, the research center combines the parameter sets together and sends back the updated parameter set. So one set of parameters, which is a combination of all the local parameters from the previous round, back to the data owners. And the data owners do this whole cycle again and again until the system converges. So this will solve part of the problem that we had for the privacy, namely, we don't force people to share data with the research center. But is it private? The answer is no. And there are some privacy risks in this whole scenario. In the training phase, you could have privacy risk that on the data. So there could be unauthorized access to the data. Your clinic, so the data holder, the clinic or the patient could be malicious, so they could be actively poisoning the parameter set to change the outcome of the big model here. You could have somebody intercepting your communication and changing the parameter set to what they want, basically, again, to change the outcome of the global model. And you could even have a malicious research center, which would, it has access to all of the parameter sets from different data owners and could do whatever it wants to kind of affect how the model would behave in the end after the training is done. So these are the privacy risks in the training phase. But even assuming that all of these are, kind of mitigated somehow, so it's in a closed system and we trust everybody and nobody is going to do anything malicious during this phase, then you come to the inference phase. So in the inference phase, the connection between the research center and the data holders is severe. So you don't have access to data. You didn't have access to the data in the beginning, but you don't have access again to the place where the data is residing. You only have your fully trained model, and you want to expose it to the outside world. So, for example, if you have a classification model, you want to let other people use it. You want to plug it into another system. So, for example, for medical use cases, it could be a decision support system. But this is not safe. So although the training process was safe, there are still privacy risks, and people could use methods to circumvent your uh, defenses to gain some knowledge about the training data or the model itself. Which brings me to privacy attacks against machine learning models. So how can we actually, before going into the privacy preserving machine learning, how can we uh, exploit the unprotected machine learning systems and gain some insight from? So for privacy attacks, there are a bunch of variables there. So for example, what kind of access level you would have to the model or to the system. You could have white box access. For example, in my previous setup, when you are a hospital and you are the malicious party, then you have white box access to your local model, maybe to the global model. You could have black box access, so you're outside the system. You don't just have access to the inference API of your model. And you could have some kind of in-between access level. There is prior knowledge, so knowing the model type, the architecture, the training strategy, the hyperparameter tuning strategy even could help you, do a better attack. Knowing the domain of the training data, the distribution of the training data, or any other type of statistical insight about the training data could also help you. And access to a representative data is in most cases a very important factor in the attacks being successful. But nevertheless, you have four main types of attacks against the inference surface of the machine learning model. And keep in mind that, for example, poisoning attacks happen mostly during the training phase. I'm not talking about them. I'm talking about when the training is done and you want to publish your model, either to hand over your model to somebody else, or even not so they don't have access to your parameters. They just have access to the inference API in the inference output of your model. So this is the same federated learning scenario that I described before. This is from a paper that we're doing a review on attacks against machine learning systems. And as you can see, here are the participants. So these would be the hospitals, and this is the research center. And these are where the attacks would happen. So you have four main types of attacks. The first type of attack is membership inference attack. And the goal of membership inference attack is, the attacker has access to a sample record. So, for example, if it is a medical use case, they have access to the medical record of one patient, and they want to know whether that patient was part of the original training set or not. So this is an inference about something about the training data. This could be a white box or black box attack, and this also works on generative models. So part of our work from our focus right now is on generating privacy-preserving datasets, synthetic datasets, and this is very important for us to protect against membership inference attacks. The next type of attack is reconstruction attack, when your aim is to reconstruct the training data itself. So you want to fully recreate the training data that you didn't have access to begin with, but from perspective of an outsider, so an attacker, maybe somebody outside your organization. And you could either reconstruct the data itself, so exactly the data, or a representative of the data which would serve your purpose. And we actually tried this on a face recognition system, and it works. It fully works. So we were able to reconstruct an image of a face of a person which was part of the training set fully without having access to any kind of prior information. There are model inversion attacks, which try to reconstruct the training model. So this could be a standalone attack when you want to, for example, steal the intellectual property of a company or somebody. Or it usually is used in combination with other types of attacks. So, for example, for membership inference attack, usually many of the more sophisticated attacks would first create a knockoff model, so a model that is a copy of the original model, and then use that model to perform, for example, the membership inference attack. There are two subtypes of attacks here. For example, you could have the task performance extraction when you want to create a shadow model or a knockoff model that would perform the same as your original model on the original test set. So on the same test set that the original model was tested on. So this is for validation purposes. And you have the high fidelity extraction where you don't want it to just work well on the if it was tested on the same test set as the original as the original model, but you want it to generally work okay. And this could be so in this case you're just trying to learn the decision boundary of the original model as accurately as possible. And this could be the case that you're not even for the copy models, for the shadow model, you're not even using the same architecture or same model type as the original model. So for example, maybe your original model is a decision tree and your knockoff model is a deep learning model. So these are all possible. And there we have the property inference attacks, and these want to learn something about the data that was not explicitly encoded in the original model. So for example, let's say you have a classification model on your customers, right? And what the property inference would like to, so the input data for each sample for the input data was for example, purchase from the KLab, so one ticket or whatever you have. What the attacker would like to know is the ratio of, for example, intercontinental flights against the domestic flights, for example, or I don't know, something like that. So this information, this ratio was not explicitly encoded in your model, but there are methods to extract that information from your model. So these are the four main types of attacks against, the inference API, so the inference surface of your machine learning system or pipeline. There are contributing factors in the vulnerabilities of machine learning systems against these kinds of attacks. So not every model is vulnerable against every type of attack 100%. Overfitting has a very large role in this in the success or failure of attack. The architecture, based on the architecture, you could use different attack models. Some attack models don't work quite well for the type of architecture, the kind of use case that you would have for your machine learning model. The access level is very important. The available public domain information. So, for example, what kind of model you're using, the domain of the input data that was used to train the model. The distribution of the data itself is again very important. And again, this is a very interesting subject that we are focused on right now. And simply put, if you have a data, so you have a data set with a distribution where most of the samples are kind of concentrated in a very small area of the probability distribution of the data, and you have some samples that reside on the long tail of distribution, so you have a long tail distribution. If you want your model to perform well on all of these samples, and based on what kind of, for example, loss function you have, or what kind of metric you would get for the use for the performance of the model during the training, the model might be forced to memorize those samples because they don't have the same necessarily adhere to the same pattern as the other samples in your data sets, the one in the concentrated area of the distribution. So the model would remember or memorize these samples, and this is very dangerous for you. So, for example, if this is in a medical use case, and you can assume that most, for example, for a specific disease, most of the people in your data set would not have that disease, and only a few people would have, and those people might be the ones who reside on the long tail of distribution. So the model would memorize the data for those people, and that's a very bad thing that we don't want to happen. And the last thing is query budget. So the query budget is simply how many times you can query the target model. So some of the a few of the attack methods that we've reviewed put a limit on the query budget, so and they have a realistic notion of how many times you can query a model without a network administrator or a system administrator realizing that they are under attack. But others don't work in this way, and we did implement one attack against one specific machine learning model, which worked quite well. So we were able to reconstruct the data like 96, 90%, 97% accuracy. This was image data, but it needed 2 million queries. I think, yeah, somewhere around 2 million queries to be able to do that. And that is not a realistic, assumption about the real world. But in any case, this is a very important factor here. So what I'm trying to tell you is that, as I said, there are factors that would set the level of weakness that your model would have against this kind of attack. The generic workflow of an attack is like this. So this is very generic. So just you can already imagine what's going on here. So this is the victim model. This is the one that we're trying to attack. It has a data set, it has inputs, it has features and everything. And there is an inference API here. And this is the attacker. So this area is for the attacker. And what the attacker does is they create this kind of knockoff model. And they have usually a helpful data set. So the data set that has, for example, the same schema as the training data set or the same statistical properties of the training data. And what they do is they use this data to generate an input for the victim model. So, for example, let's say for the face recognition, you would just generate a image that would resemble a face, and you would send it to the victim model. The victim model would tell you, for example, the level of confidence it has that if this face belongs to this person, that person, and based on the answer that you would get from the victim model, you would, train your attacker model. So the attacker model would be able to generate the perfect sample that if you would get to the victim model, it would tell you with 99% accuracy, this is an image of this is a face of Saba, right? So in that point, you have successfully trained a generative model that would be able to generate my data. So my data, the data of my face is encoded in that model. There are other types of attacks. There are different workflows, but the generic workflow is something like this. This is very interesting. Again, this is based on our work. So what we did for this one is we trained a very simple digital recognition model, a convolutional model on MS data, and then we performed a reconstruction, an inversion attack. So we try to have a model that resembles the target model as closely as possible. And then we fed it some data, and this is the output of the victim model. So the top rows are from the victim model, and the bottom rows are from the knockoff model. And this is the output of the first convolutional layer of the model. And as you can see, the outputs are very closely resemble each other. So after some adjustments, you would get with the weights and everything, you would get almost the same representation of the input data from the target model and the victim. This is another one. Again, this is scary accurate. So this is from a 2020 paper named Disco. So these guys present another method to prevent this kind of privacy attacks. But the interesting thing is this result. So on the left side, you see the training data. So these are just images of faces. On the second column is the reconstructed data using a specific type of attack against an unprotected machine learning system. And as you can see, they were able to almost identically reconstruct the data that was used to train the model. And the right three columns show the same type of attack against on that model, but now that model is equipped with some kind of protection, so privacy protection or privacy preserving mechanism. For example, they have adversarial methods, they have random methods, and this is discover their own method. And as you can see, when you add that privacy preserving measure to your system, to your machine learning system, suddenly the attacker is not able to infer something or extract something from your model, so the output of your model. The details are not important at this point. So there are, and this is not the only paper. So there are a lot of papers on both the attacks and on mitigation methods to prevent these kinds of attacks. But the point is that if you don't use privacy preserving mechanisms, there is a high risk that your data would be leaked. So how do we stop these privacy attacks from happening? There is data anonymization. Data anonymization is very popular, especially in the medical domain. So for the ethics boards and committees and everything, usually when you anonymize the data, they feel like it is enough to release data in some capacity, limited amount, but it is not enough. I won't go into details of why these won't happen, but there are famous cases, for example, the Netflix case, where people were able to de-anonymize the anonymized Netflix data. There's a medical case in North America, but long story short, the data anonymization doesn't work. Just a quick pointer, a few pointers on why that doesn't work. The first and most important one is linkage attacks. So linkage attacks try to use another dataset that has another public dataset that has some kind of connection with your anonymized dataset to de-anonymize your data. And the point is that when you change your dataset to make it privacy preserving, you cannot control what other datasets are published out there. So might be right now your dataset there are no related datasets published and your dataset is anonymized. But if you maybe in the future somebody would publish another dataset which would have some kind of prior connection to your dataset, and then people would be able to use that dataset to de-anonymize your data. There's a priori knowledge of the knowledge that you would have beforehand from the statistical features of your data would be very important in de-anonymizing the data. And then there are composition attacks, which basically work like this. So if you release a k-anonymized table once, it is anonymized or private to some extent. But if you do it a second time, a third time, every time you release that data, the level of privacy is reduced a little bit. And there are methods who would actually exploit this kind of continuous release, which are composition attacks. Yeah, but data anonymization doesn't work, so you cannot just assume that you would keep anonymized data to your machine learning system. Output perturbation also could work, but if you want to have really high levels of privacy, you would need to add a lot of perturbation to the output of your machine learning model, which would have a serious impact on your utility. There are regularization methods, which actually, this is interesting that when you add differential privacy, in many cases, it works as some kind of regularization method. So we were able, for example, in one deep learning model, we were able to remove the regularization steps and just add differential privacy, and we would still get a very high level of utility. And then you have differential privacy, which is a set of standards that would help you achieve privacy in your machine learning system. And with that one, I would like to stop and ask if there are any questions up to this part of the talk.
Hi, Saba. There are no questions so far. There was only a remark that sometimes the sound is not received that well. So maybe speak clear. But I think for most parts we're quite okay, but it's maybe something to have in mind. But at
Yes,
this moment, there are no.
yeah, sure. Just let me know if the sound drops again, because I'm using these earbuds and there are no noises in the environment. But yeah, that's it. Okay, so scary stuff behind us. We know that the machine learning systems are vulnerable. I would encourage you to just search for privacy attacks against machine learning systems. There are a bunch of papers, even commercial packages on GitHub or whatever else that would actually help you perform attacks against machine learning systems. So, and I said that again, among different sets of methods or ways to achieve privacy preserving machine learning, differential privacy is a very viable method. So, before giving you the actual definition, so the mathematical definition of differential privacy, what differential privacy is a set of standards uh, not the actual privacy preserving mechanism. So it's not like, for example, applicate perturbation. You would use some kind of perturbation mechanism to achieve differential privacy. But differential privacy is a set of standards that if you adhere to, or if your machine learning system adheres to, you could say with mathematical guarantees that your model is privacy preserved. Differential privacy is a property of the randomized mechanism, so your machine learning model, not the data. So this is the difference between using differential privacy and using data anonymization, because the data anonymization is applied on the data, but here you apply this standard or embed this standard in your mechanism. What differential privacy tries to do is it tries to provide plausible deniability, meaning that an adversary cannot infer something about one member of your or one record of your training data set with a high level of confidence. With differential privacy, what you would do, so these are all different definitions of differential privacy from different angles. With differential privacy, what you try to do is you try to learn as little as possible about any individual member, while you learn useful insights about the population. So this is what we would usually do. There are two main types of differential privacy, local and global. Actually, there's multiple differential privacy, but I won't go into that in this talk. The global differential privacy is like this setup that I presented to you. So you have data holders. So let's assume that these are patients with a tracker, fitness tracker, and a small private data set of their vitals. And you have a trusted arbitrator here would be that arbitrator would be a hospital, and the patient trusts their data with the hospital. But now the hospital wants to publish that information somehow or use that information somehow. For example, like the federated learning scenario that I gave you. So they want to use that data to train a machine learning system, local machine learning system, send the parameters of the machine learning system to the central server, to the research center. And we have learned that it is not safe to assume that if you just send the parameters of the machine learning system, it will be private. So your data would still be at risk. So this is the global differential privacy paradigm. You have local differential privacy paradigm where there's no trust between the data holder, and there is actually no trusted arbitrator. So you need to have sample level differential privacy. In this talk, because it is more related to the domain of the work that I'm doing, the consortium, the API consortium, I will talk about the definition of global differential privacy, but it could be very easily extended with just minor adjustments to local differential privacy. Differential privacy is very robust in the sense that it is context-free. It doesn't rely on any kind of specifics of your machine learning system or machine learning model method. The adversary, so what the adversary wants to do or will intend to do in the future. The data that you're using to train your machine learning system. So it doesn't rely on any of that. But because of this robustness and this generic kind of notion that it provides, there is a high privacy utility trade-off or a very delicate privacy utility trade-off that you need to be mindful of. So keeping this in mind, now let's go to the definition of differential privacy. So before giving you the actual definition, consider two datasets, S and S prime. We call these two datasets adjacent or neighbor datasets if they only differ in one member. So you have a dataset of your customers, and you have S and S prime and S prime. The only difference between S prime and S is that S prime doesn't have the record of one of your customers, right? This would be the definition of two adjacent datasets. Now, what differential privacy is differential privacy says that if you have a randomized mechanism, so let's say this is your machine learning system, right? And you apply this randomized mechanism on these two adjacent datasets. So, for example, you train your machine learning system on dataset S and S prime. It says that the basically and the epsilon and delta differential privacy. So this is the definition for epsilon delta differential privacy. It basically says that the probability distribution of the output of the mechanism trained on dataset S should not be more than e to the power of epsilon multiplicative e to the power of epsilon different from the probability distribution of the output of that same model but trained on dataset S prime. And keep in mind that these are randomized mechanisms, random mechanisms. So, for example, if you have a classification model, what you're trying to do, if you have your data X and your label Y, the output of that classification, simple classification model, would be the probability distribution. So the distribution of output would be the probability distribution of Y given X. And you could have the same kind of interpretation for any kind of machine learning system. And what basically here, this definition here means is that the log likelihood ratio between the output of these the same mechanism trained on two different data sets is bounded by epsilon. So this is very simply the definition of differential privacy. The bounds on differential privacy, as I said, are applied over the randomness of the algorithm. And when the privacy budget is actually small, so even when the epsilon is small, and keep in mind that the smaller your privacy budget is, the more private your algorithm will become. And when your epsilon is very small, then the distribution of the output of the two mechanisms or the same mechanism trained on two different data sets, two different adjacent data sets, are almost the same. And this means that you have a very high level of privacy. So you have provided that one sample that was not present in your first data set with plausible deniability, but you haven't learned anything useful from that one sample. So the goal is that you gain useful information from all of the samples in your data set. And since this could, be applied for any sample in your data set, if your, for example, epsilon is very, very, very small, then you basically have a high level of privacy, but no utility whatsoever. So the parameters of differential privacy are epsilon and delta. The epsilon is called privacy budget. Actually, the first version of the first definition of differential privacy was just epsilon differential privacy. Then delta was epsilon delta differential privacy was provided as a relaxation of the original differential privacy definition of differential privacy. And I'm using this because then I will use the same definition for the actual deep learning. So how do we achieve differential privacy in deep learning? But before doing that, let's just focus on the parameters of differential privacy. So you have the epsilon, which is the privacy budget, and this controls the trade-off between your privacy and utility. The higher epsilon, so the higher the value of epsilon, the lower level of privacy you would get. And there are high privacy regimes, there are low privacy regimes, but I read somewhere that a industry-wide rule of thumb is that it is for very big data sets, it is okay to have epsilons of up to 10, but after that, you basically have no privacy. But it is not always the case. It very much depends on the type of task that you do, the type of machine learning that you're doing, number of samples, and many other factors. But usually a good value for epsilon would be somewhere around 1, so a little bit below 1 or a little bit over 1. Again, these are just rules of thumb, so it is case by case, it will be defined. And the delta is the probability of the differential privacy fading. So this is a small probability mass that you would throw at the probability distribution of your the output or your mechanism. And with this probability, this small probability, your method would fail. And the reason why it is here is because this lets us do a lot more with the definition of differential privacy in our data processing. And again, a rule of thumb is that the value for delta is cryptographically small. So, for example, at least they usually, in many examples, they would set the number for delta to be at most 1 over the number of samples. So if you have 10,000 samples, your delta should be less than 1 over 10,000. So this is the definition for differential privacy. How to achieve differential privacy? It is usually by perturbation. So introducing some kind of perturbation to your machine learning pipeline. And mostly this perturbation happens by adding noise. You could add noise to your input data. You could add noise to your to the parameters of your machine learning system, or you could add noise to the output of your machine learning system. Adding noise to the data, to the input data, and to the output of your machine learning system has proven to be, up till now, has proven to be very costly in terms of utility. So the most successful method to add differential privacy to a deep learning system or machine learning system usually works with adding noise to the parameters of the system, but that is not, again, always the case. There is a paper from 2017 that they use this affine transformation layer at the beginning of the deep learning system that does a differentially private PCA. So they do dimensionality reduction and they add differential privacy at that stage. So yeah, but that's another thing. So, but how to achieve differential privacy? The most simple method to add perturbation to the output and to achieve differential privacy is Warner's randomized response. I brought it here because of 2 reasons. The first one is that it has been proven in 2016 that it is the most efficient method to achieve differential privacy. But it is not always applicable in real world situations. So it's very hard to adjust it, for example, for a deep learning system. And what randomized response does is that you are asked a yes and no question, and you are given 2 coins. The coins could be fair coins or unfair coins. So what you do is you flip the first coin. If it is heads, the result is heads. You answer truthfully. If the result is tails, then you flip the second coin. And if it is heads, then you answer yes. If it is tails, the answer is no. And it can be proven that this is actually achieves differential privacy. And you just need to know the level of bias in the coin. And this is a very interesting example that I got from 2017 talk from Google. You could see the original talk and the source here. So this is a printout of the Mona Lisa, and the way they did was they created this as a binary photo with M's and dots. As you can see, this is all M's and dots. And then what they did was they applied the randomized response method that I told you before to this image. So for each pixel or each dot or M, they put it through that randomized mechanism, and they decided whether to answer truthfully or to just put a dot or an M in place of that pixel or that point. And this is the results of applying randomized response to the Mona Lisa. And as you can see, this is actually the whole thing about plausible deniability and learning something about the population without learning about specific samples here, specific pixel. This is exactly is shown here. And well, you see that you can kind of have a big picture definition of Mona Lisa, and you see the main points of the painting, but you cannot really know anything about specific points in the image. So you cannot be sure, for example, for this one or this point or any of the other points. So this is the randomized response method. There are other primitives that you can use, and most texts for differential privacy actually start with Laplace noise. So what you do is you draw a sample from a Laplace distribution, and you add that sample to your to the output of your query. For example, if you're doing let's say you're doing the count, and that would be it. But here I'm going with Gaussian mechanism because Gaussian mechanism was used later for adding differential privacy to a deep learning system, and that is why I'm going straight for Gaussian differential privacy. So again, we have the parameters epsilon delta for differential privacy, and it is as easy as adding a sample that was drawn from the noise distribution and adding it to the output of your query. So let's say your query function is Q, and you want to, for example, count something on dataset S. What you do is you run the query, you get the result, and you add a sample that was drawn from this normal distribution. And as you can see, the parameters of the normal distribution are calibrated with the epsilon and delta that you have here, and you would achieve differential privacy. And then this will be used in a deep learning scenario. But before actually describing the algorithm there are some questions that need to be answered to be first to be able to fully understand how to achieve differential privacy in a deep learning or machine learning system. The first one is, how does differential privacy deal with iterative nature of machine learning training algorithms? Because the point is, anytime you access data, you incur a cost. And so anytime you access the data, your mechanism needs to be differentially private, and you need to add noise. So how would you figure in the end, if you do 1,000 rounds of training, what is the level of privacy? You have two basic composition theorems. There's parallel theorem, which basically says if you have a bunch of differentially private mechanisms running in parallel on the same data set, and you want to combine the output of them in some kind of other mechanism, the output mechanism, so the combination, would be a differentially private mechanism whose epsilon would be the maximum of epsilon from all of these mechanisms, and the delta would be the maximum delta from all of these mechanisms. So this would be the parallel. The sequential, as you can guess, is if you have mechanisms applied to the same data set in a sequence, then the epsilon would be the sum over all epsilons, and the delta would be the sum over all deltas. But this will give you a very worst case scenario bounds on your differential privacy. So with the same amount of noise, there is advanced composition theorem, which actually proves that if you do sequential combination of randomized mechanisms, the epsilon would be somewhere around the square root of the number of the mechanisms if all of them have the same epsilon. And then there is moments account and training differential privacy. All of these methods basically provide you with different ways to approach differential privacy, so that you would get tighter bounds with lower amounts of noise that are added to your mechanism, to your machine learning mechanism. The next question would be, how does differential privacy preserve the privacy of inference surface? So going back to the attacks, I repeated this several times, that what the attacks that I introduced here were attacks against the inference surface of the machine learning system. So how does differential privacy protect that surface? It is with post-processing theorem. which says that if you have a differentially product, so epsilon different delta differentially product mechanism, y, and you have another mechanism which could, let's say, this is not differentially product, and you apply that mechanism on your differentially product mechanism. So you use the output of your differentially product mechanism in some way. The output of that, this combination, so application of, for example, mechanism O and mechanism M, let's say you feed the output of your machine learning system to another machine learning model or to some other type of query system, the output would be at least epsilon delta differentially product. So very simply, if you train a machine learning system in a differentially product manner, whatever you do afterwards, it will be still differentially private. And now, now in this section of the talk, I will actually describe the algorithm for adding differential privacy to deep learning. This was proposed in 2016 by Martin Body from Google, and this was a breakthrough in adding differential privacy to deep learning. There have been other methods, more recent papers that provide better, maybe not better, but maybe more efficient ways of adding differential privacy to deep learning in certain circumstances. But this is one of the most widely used methods to achieve differential privacy. So what DPSCD does, so this is differentially private stochastic gradient descent. The contributions of the paper was first they created this algorithm for adding noise during the training phase to the gradients that they calculate for training the machine learning system, and then they proposed this moments accountant, which basically is an accountant that would calculate the bounds of differential privacy, the bounds of noise, the bounds of privacy that you would get with the same amount of noise, and this will give us a very tight noise bound, which will let us, which will lead to having us being able to claim better differential privacy levels with the same amount of noise being added to the gradients. So what happens here is that first, so this is like a normal differential privacy. This is a normal stochastic gradient descent algorithm. There are actually three different differences between this one and the normal algorithm. The first one is here is the clipping. So what I didn't describe in the previous section was the sensitivity of the mechanism. So to achieve differential privacy, you need to know the sensitivity. And the sensitivity, the definition of sensitivity is that if I apply the same mechanism on two neighbor data sets, S and S prime, what is the maximum amount of difference between in the output of these two mechanisms? So the maximum difference would be your sensitivity of your query. So for example, for a count query, the maximum sensitivity would be 1 because if you're using, for example, if you're counting consumers or customers in any way, the difference would be mostly 1 because you're counting one by one. So what you do is, first of all, because the gradient cannot be bounded, so you cannot assume that your gradient is, for example, less than a certain number. What they do is they clip the gradient using this parameter C, and this C will then be the sensitivity of your query. So this is the first step. The second step is to add noise. Then when they want to calculate the gradients, they add a sample drawn from a normal distribution to this vector of gradients. And again, as you can see, this is calibrated by epsilon and delta, which are parameters of differential privacy. And then the rest is the same. They do the descent and they do this training ground, and they have shown and they have been shown again and again that this is a very good way to add differential privacy to a deep learning task. The third one, which I didn't mention, and I didn't want to go into details because I really think I'm over time, is the application by subsampling. So what differential privacy says that if you apply your mechanism not on the whole data set, but on a subset of data set, then the amount of privacy budget that you will spend will be less than the whole if you were running it on the whole data set. So it will lead you to spend less privacy budget for each round. So what they do is, first of all, you're doing stochastic gradient descent. So for each step, you're taking the subset of the data, and then they have this thing called a knot, which basically like they're sharding the mini batch, and then they are running the algorithm on those shards, which will lead to better privacy bounds for the algorithm. So yeah, so this was my very short presentation on differential privacy and on how to achieve differential privacy in deep learning. I have one more section which is differential privacy in practice. But again, if there are any questions, I would be happy to answer them.
All right, Saba, I think there are no questions in the Q&A. So there was a question from Cindy Bennett. How do you add privacy to the data processing instead of the data itself? Can you give an example? I think that was, let's say, what you will just discuss with us.
Yeah, yeah. Okay, so I think I was successful in making it. All right, so yeah, so all right, so all of these theoretical stuff is very interesting, and you can see a lot of very good papers, even books on differential privacy. But how do we achieve differential privacy in practice? So in practice, first of all, the theory is straightforward, but the implementation is hard. So for example, a very simple thing like what kind of noise that you're using. If you're using Laplace, you can have different privacy budgets, so different epsilons. But Gaussian mechanism, the way I presented to you, was just for epsilons, for a high privacy regime. So for epsilon less than 1. If your epsilon goes more than 1, then using Gaussian mechanism will give you wrong bounds on your nodes, and that is not good. So for that one, for example, you could use something like the analytical Gaussian mechanism, which kind of clips or use some kind of clipped distribution. But yeah, that doesn't matter. The point is that you need to be very careful when you add differential privacy to your machine learning system. The second thing is that it changes the dynamics of your machine learning pipeline. So, for example, mostly, let's say in the KLM, you have a lot of machine learning systems. You have designed your deep learning system or random forest, whatever you have, and you have fed it the training data, and you have a trained model. When you add differential privacy, first of all, you need to retrain your model, obviously, because the mechanism has changed. The second one is that it kind of changes the behavior of the model. You cannot really measure how much it changes the dynamics of the system before you actually do the training. But you will probably need some kind of hyperparameter tuning, or maybe even redesign your system because this suddenly doesn't work. For example, based on the distribution of the data, this could be the distribution could have a very big impact on the performance of the system. But on the other hand, there are differential privacy libraries that have been matured in recent years, which will make our lives much easier when we want to just, play with this definition of differential privacy, or gain a more or gain a deeper understanding of what it does. So what you need to figure out to add differential privacy to your pipeline, first of all, is your noise adding mechanism. So what kind of primitive are you using to achieve differential privacy? Are you using randomized response? Are you using Laplace noise, or adding Laplace noise? Are you adding Gaussian noise, or any kind of other perturbation mechanism? You need to fix your privacy budget. So what maximum amount of budget that you would get? What is it, for example, based on your use case? For example, you could go with a higher, delta is almost always known, so you would fix the delta to be a very low number. But for epsilon, you could go with a higher epsilon or with a lower epsilon based on the needs of the system. And then you need an accounting method that would give you the privacy bounds for the amount of noise that you add. So, for example, if you use Rennie differential privacy, or you use Moments accountant, or you use advanced composition theory, with the same amount of noise being added, let's say in the stochastic gradient descent, so the DPSUD, with the same amount of noise, they will give you different bounds. So, for example, one method of accounting or calculating the privacy bounds will tell you that your epsilon is 2. The other one would tell you that your epsilon is 1.5. The other one would tell you that your epsilon is 1.2. And the difference is that they use different theoretical basis to calculate the bounds, and some of them are able to calculate a tighter bound for your privacy. So right now, the way I see it in different repos and different papers, most people are inclined to use Rennie differential privacy, which is a little different from the original epsilon delta differential privacy. So they use Rennie divergence to define differential privacy. But yeah, again, the basic idea is the same, and I will show you that in a little bit. So there are two main libraries right now that I know of that provide you mainstream libraries that provide you with different privacy. The first one is TensorFlow privacy. So this is an extension of the famous TensorFlow library. And how to add differential privacy to an already existing TensorFlow pipeline is very simple. I took this code sample from one of the examples of TensorFlow privacy. I removed some of the code which is obvious for somebody who is knowledgeable in the framework, so it's quite easy. But the difference is this. So first of all, you have a couple of three imports here. So you import the RDP accountant. So this is Rennie differential privacy accountant. So the counting mechanism that you have, this is compute RDP, and then you import this get privacy spent function. And then for the model, you will import a DP sequential model. So this is exactly like the sequential model of Keras, but this is the differentially private version. Then you have several parameters here. So the first one is the noise multiplier. This basically tells the algorithm how much noise it should add in each step. You have the clipping, so the C parameter that I told you where to clip your gradient. Again, this could change based on the type of data that you feed to the model and the type of model that you would have. And you have the batch size, which is related to your privacy by application by subsampling in privacy amplification. And then they define this compute epsilon function because, as I said, anytime you access the data, a privacy cost occurs and you need to spend a little bit of your privacy budget. So basically, to calculate how much budget you have spent, you just need to know the number of steps that you have taken, so the number of iterations. And they define this function, this load and user, just load the data. And for the model, as you've seen, you don't define a sequential model, you define a DP sequential model, which takes these additional parameters, the clipping threshold and the noise multiplier, and the layers have been defined before. These are the same layers, convolution and whatever. For the optimizer, you just use a normal optimizer. And the loss also, for example, this one is a category called cross entropy. You compile the model, you feed the model, and then the last thing would be to just call this function that we have here, and it will give you for a fixed number for delta. So we have defined the delta before the current epsilon, so the current privacy budget. So the amount of privacy budget that you have spent up till this point. This is a very simple example of adding different privacy to TensorFlow privacy. The address is here, so, fancy code, but you can just search TensorFlow privacy and go to the website. The other one is Opicus, and Opicus is a library by Facebook. So this one works for PyTorch. So in previous slide, we were working on TensorFlow, and this one is for PyTorch. Again, this is maintained by the same company, but yeah, adds differential privacy, and it is actually much more intuitive than the previous one. What you do is you define a model, you define an optimizer, and then you define a privacy engine. So the privacy engine would take the same parameters as the previous one, so the previous slide that I showed you with TensorFlow. So you have the sample rate, you have the alpha, so this could be translated to epsilon differential privacy. So this alpha is the parameter for any differential privacy, and any, as I said, is a different interpretation of differential privacy. But there is a way to convert the alpha to epsilon and back. So there's a very simple formula. You have your noise multiplier, and you have the clipping threshold. So you define this privacy engine. And then you attach the privacy engine to the optimizer that you're then going to use to train your model. And that's it. That is the whole thing that you need to add to your existing model to achieve differential privacy in PyTorch. So yeah, this was my slide for the practical aspect of adding differential privacy to your models. Do I have like 5 minutes to go over and introduce our own research, or no?
5 minutes maybe, but if it's it's a bit past 5, so I see people already leaving. But maybe let's say if you have only 5 minutes,
Yeah.
just to go ahead.
That's okay. So let's stop for now. I'm always very happy to discuss our research with other people. So my email is at the first slide of this presentation. If you're interested, please reach out to me. I would be more than happy to discuss this with you. But I think this is a good time to stop the talk.
Okay. Well, thanks for the presentation. So it's really an interesting topic. Some parts really technical, but I think the main message I think is quite clear, at least for me. So maybe time for question and answers. So there were no real questions yet. So there was one question from William van de Kamp. He said, interesting presentation. So I agree. What is your view on the future of privacy preserving machine learning?
Let's see. Well, the field is very hot right now, so there's a lot of research in theoretical computer science and more applied computer science in achieving differential privacy or privacy preserving. So privacy preserving machine learning. So it's not all differential privacy. I'm focusing on differential privacy as a very good solution to achieve differential privacy, to achieve privacy preserving machine learning, but it doesn't do everything, so it doesn't protect you against all types of attacks. And I think that in the future it will be extended a lot more. And keep in mind that right now our data is in the hands of big companies, and unless you have very good laws and regulations in place to preserve the privacy of the data, then the data is vulnerable. There could be the potential for data leaks. And you need to and most of this data is used for some kind of data processing mechanism, and you see that more and more the data is fed to a machine learning system. So I think one of the most interesting aspects of achieving privacy in this data-driven world would be to add different privacy, or to add privacy preservation capabilities to machine learning systems. But I think this will have a very interesting future.
Okay, thanks. I have one small question myself. So I was wondering, so you talk about a text. Is it possible to in some way detect that your model has been attacked?
Depends. If you're just talking about the attacks that I told you, so these attacks are just for the inference API of the model. So these attacks almost always work with some kind of query being thrown at your model. So either you need to have for example, if I am a attacker and I have a certain IP address and I'm sending you like 1,000 requests every minute, you can easily detect me as an attacker. The other one would be to detect the adversarial queries, because, for example, if you have a face recognition system and you have for example, a camera and people are coming into the KLM and the camera detects who this person is, for example, each person has a very different set of facial features. So different queries, so sequential queries would have very different answers. But if you detect that there are queries that by time are very similar to each other, it's like one person with very different, with slight difference in facial features is coming again and again through the door, then you can detect that this person, there is an attack going on. And actually, I think I read a paper a couple of months ago that actually tries to do that. So these are the two ways that I can think of to protect against attacks on the inference API. For poisoning attacks and other ones, there are other methods.
Okay. Well, thanks for your answer. Thanks again for the presentation. So really very interesting. And if people still have questions, I think they can contact you. So your slide deck and also the recording will be found on the SharePoint page that we put in place for this. I think people can look back and also contact you. Maybe some last remarks before we close. So we will have now our summer break and we will try to continue in September. So still, let's say, looking for, let's say, the speakers. We have some topics. So for now, enjoy your holidays and I hope to see you in 2 months again. So thanks, and I will now stop the broadcasting.
Thanks for having me.